Form 7 Physics, Unit 4, third term content, electric field strength. The content in this video, I have included the facts related to spec point 95, that is, use the equation E equal Q over 4 pi epsilon 0 R squared for the electric field due to a point charge. And the spec point 97, use the equation E equal V over D for an electric field between parallel plates. First, we will focus on electric field strength due to a point charge. Here, positive charge, that's I have labeled it as plus Q. Here another positive charge, I have labeled it as plus simple Q. The separation between the two charges is R, simple R, separation. Then, as you know that this is a positive charge, this is also a positive charge, so the force will act on each other, repulsive force, which is given by the Coulomb's law, that is F equal K Q over R squared. So the force act on each charge is denoted by the capital F, and this force is equal to this force. That is as the both are Newton third law pair. The force act on capital Q is equal the force act on simple Q by capital Q and by simple Q on capital Q. So consider the charge plus simple Q at a distance simple r from a charge positive Q. The force F act on charge simple Q by capital Q. Charge on this by capital Q charge. So what is the force? Is this force is given by K, the product of the two charge QQ, and the separation squared. Separation is R from their center to center squared. So the electric field strength, if we consider the electric field strength from R distance from the capital Q charge as E, so the expression can be given as F over Q, charge per unit charge. So if we rearrange this equation, F equal K Q over simple R squared. So if we bring down this Q there, this is this charge. So we can rearrange as F over simple Q KQ over R squared. What is this F over simple Q? Is the force per unit charge, that is field strength. So we can finalize the relationship as electric field strength equal charge capital Q over 4 phi epsilon 0 R squared. Instead of 4 phi epsilon 0, we can use K, Coulomb's law constant. So then it will be capital E equal Q KQ over R squared. 1 over 4 phi epsilon 0 is the K. So further, if I explain it further, you can understand for any given charge. Now this relationship is very important to find the electric field strength act on a unit charge at a distance r from any charge. Now this can be Q, so it can be any charge, Q1, Q2, whatever. The electric field strength at a distance r will be given by this relationship. So basically this relationship you can use to find out the electric field strength at a distance simple r of a point charge. Uniform electric field. Now we have little bit learn about the uniform electric field, about how the field line patterns and all. So this this diagram is little bit familiar to you. Top plate, bottom plate, and this both metal and positive charge on top, so that's why the field lines down, and as this is negative, field lines towards it. The potential difference between the two plates is V, and the separation of the two plates is simple D. So the electric field strength relationship is given by as capital E, electric field strength equal potential difference of the two plates divided by the separation. So uniform electric field strength exists between the two charged parallel plates. As this is parallel, you have to understand that is uniform electric field. So the separation is D, so potential difference is V. So electric field strength is given by V over D. So when it comes to V over D, you have to understand that V is the potential difference, unit is volt, the separation D is the unit is meters. So the another you will come across now here, you will come across another relationship for electric field strength other than NC minus 1 Newton per Coulomb, volt per meter, volt per meter. Let's consider motion of a charged particle in a uniform electric field. So here the pathway is given. Here it enter a positive charge of mass m with the velocity, it's enter horizontally. So here the region of uniform electric field, how we can say it uniform, because the field lines are parallel and equispaced, and as the field lines down, we can predict the charge of the top plate as plus with our knowledge that we have gained earlier what it is, as the electric field lines start from positive and ends at negative. So this will be the negative plate and this will be the positive plates. Let's proceed. So electric field lines directed down, so we predict that before. Field lines move positive, as field lines move from positive to negative, and so top plate is positively charged and down plate is negatively charged. And as electric field strength E, we have come across that also in the earlier video, electric field strength E is a uniform electric field, so electric field strength is same in everywhere. Electric field strength is same in everywhere. So as the force act on a charge is given by F equal EQ, so E here is constant for the uniform electric field. So if the charge also constant, what we can say, the force act on a charge Q anywhere in the field will be the same, or we can say it is constant. Let's analyze this situation. So the charge particle here, when the charge particle enter, it enters through to a electric field. What is electric field? The force is act on a charge particle. So here what we can expect to have a force on the charge particle. Force is a vector quantity and it has a direction. So what direction the force act will be the direction of the electric field strength or the electric field direction. But why the electric field direction is down, as this is the positive plate and this is the negative plate. So as F equal EQ, as F equal EQ, the direction of the force will be the direction of electric field E. So we can apply linear motion equations either downwards or vertically down or up or horizontally. So the two dimensions that we can apply the linear motion equations are horizontal direction or vertical direction. So what will be the motion now? Now as the particle enter horizontally and the force act vertically, so there won't be any force act on the charge particle horizontally, because there is a 90-degree angle between the horizontal and the force line direction, force acting direction. So when we resolve the force 90 degrees, it's become 0. So no horizontal force act by the field on the moving charge, as the charge is entering perpendicular to the field. So now if we consider the vertical motion, or along the direction of the field, so if it is a positive charge, then positive charge will accelerate along the field line. Now if it is positive charge here, so field line down, so here this plate is positive, positive, positive repel, so it will move down towards or along the field line, it will accelerate. Why I am telling it is accelerating? As the electrostatic force that act on the charge which is in the field is experienced a resultant force. So when a resultant force, what is the resultant force will be? Resultant force will be the electrostatic force that act on the charge, that is F equal EQ. So the negative charge will experience acceleration along the field line towards the field line direction. And if it is negative charge here, now think of the negative charge here. So the negative charge will attract by the positive plate. So it will experience resultant force or the electrostatic force, that is build the resultant force towards the positive plates. Then it will be opposite direction of the field line. So you have to keep that in mind. Then motion can be divided into two components, as what we have learned in AS. So motion is parabolic between plates. Why it is parabolic? Because horizontal motion and vertical motion is there. So as the horizontal motion and vertical motion exist, horizontal motion, the acceleration is 0, and then acceleration is 0 means constant velocity as no resultant force act, and vertically there will be acceleration, so the velocity increases. So that's what I have mentioned here, this horizontal and vertical motion independent, but you have to keep in mind, parallel to the field line, the particle undergo acceleration. It can be up, it can be down, depending on the charge that enter. But it will be whatever the charge enter, it will not act any force horizontally, as field, then the force is perpendicular to the direction of motion. So acceleration will be 0. So it will move with constant velocity horizontally. That is what is mentioned here. Now let's think of work done on charge particle. Work done on charge particle. When a charge particle moves through a potential difference, we have learned in AS second unit, or the unit 2 under electricity, but we learn how we define the voltage, or how we define the potential difference. Potential difference we have learned as work done over charge, or the energy per unit charge. So when we say the work done over charge is the voltage, so when we say what is work done is voltage into charge. So work done is voltage into charge, and work done is energy. So when a work is done on the charge particle by the field, what it gains, where this energy goes? Energy goes to gain in kinetic energy of the charge particle. That is obvious. So we can have this balance, or the equation, as I mentioned earlier, that work done is potential difference into charge, then it is equal to gain in kinetic energy. Then we can substitute the kinetic energy relationship. So when a particle gain kinetic energy means now mass is constant, gain kinetic energy means the speed increases. So speed increases, we can say that the particle accelerate. So what it causes? It caused by the resultant force that act. What is the resultant force? The electrostatic force that can be given, that is given by F equal EQ, and also we know that from the Newton's second law that resultant force equal MA, F equal MA. So when we equal this to resultant force, F is provided by the electrostatic force. So as resultant force equal to electrostatic force, MA is equal EQ. So then we will have a relationship for the acceleration of a charged particle in an electric field. So it's governed by the electric field strength E, the charge of the charged particle, and the mass of the charged particle. So let's work out an example. In one type of inkjet printer, a tiny ink droplet of mass m carrying a charge minus capital Q is steered to its place on the paper by uniform electric field. Now you can observe and understand why it's called uniform electric field. Two plates parallel and the field lines equispaced parallel. So then obvious it is an uniform electric field. So the diagram shows the path of the droplet. So droplet is negatively charged, it's moving up. Why? This side is the positive charge, positive plate, and it's like a positive charge in this place. So the negative is moving towards positive and it's accelerate along the field line, the component, right? So part A, give an expression for the acceleration of the droplet. Give an expression for the acceleration of the droplet caused by this electric field. So if we work out that electric field between plates is uniform, so this is the suitable relationship for the uniform electric field strength illustration, that is potential difference divided by the separation of the plates, and it's acting down as this is positive. So the drop with charge minus capital Q and mass simple m has an acceleration given by, as we discussed earlier. So this force is the resultant force and electrostatic force also the same. So we can replace the resultant force by the electrostatic force QE, F equal QEQ or QE. So then what we obtain, and here you can say that V over X is given by the electric field strength. Here we can replace the capital E here by V over X. What is this X? The relationship is D. D is the separation. Here the separation given as X. So we have to substitute that relevant value or the symbol for the separation. So we get V over X. So when we work out all together, so replace V over X, replace E by V over X. So now the relationship read as A equal, that is acceleration equal minus Q V over mx. So why this negative? Negative sign means the acceleration is opposite to the field, as it is negative charge. It is upwards as the droplet is negatively charged. So describe the path of an uncharged droplet. Now if the droplet is uncharged, so what do you expect? Now what is electric field? Electric field is an area or space where electrostatic force act on a charged particle. So if the particle does not charge or it is without charge, there won't be any effect from the electric field on the droplet or on the object, whatever. So we can say that as a drop with the zero charge will not affected by the electric field. So it will cross the plates in a straight line, assuming that downward gravitational force is negligible. If this is negligible, there won't be a downward motion. So it is only straight. suggest how different droplets can be steered to different places on the paper. Now we have come across a relationship for acceleration QV over mx. So QV over mx. Now here what we are going to do, how to do this, how to change this A. We can change the A by giving different charge. Now if the Q change, although the others, now V have to be kept constant and mass and X is constant, so we can change Q by giving different charges to the droplets, so the A will change. Now when A change, what will happen? It will change the vertical displacement, because vertically there will be acceleration as the resultant force act vertically. So the vertical component, there will be a displacement vertically. So displacement vertically depend on the acceleration. So the vertical displacement vary with different acceleration. How different accelerations obtained? By varying the Q or the charge of the droplet. So we will get different displacements for the differently charged droplets. So they will emerge from the plates moving in slightly different directions or the different displacements. So we can steer the droplets to different places on the paper. Let's move to the example 2. So the photograph shows, there's a photograph here, shows an arrangement for investigating charge known as the shuttling ball. Shuttling ball. But you can observe one plate, another plate, metal plates, and they are parallel. So if they are parallel, now we have to guess what the field is. Now a little bit more description. Now in exam, this is also part of an exam question. So there's a big description. Now when a description is big, some of our kids are a little bit reluctant to read. So if you are reluctant to read, it itself make you into or fall you into a difficult situation, because when the lengthier description is there, you have to read it thoroughly and much patient to understand the situation. Without understanding the situation, my dear children, you can't understand the problem. So to solve the problem, we must have a better understanding. That is same in the general life. So physics also the same. A ball coated in conducting material is suspended on a very long insulating thread between metal plates. A potential difference PD is applied across the plates so that the plate X is positively charged. So here positively charged and plate Y is negatively charged. When the ball is touched against the plate Y, it gains a negative charge. Now here positively charged, here negatively charged. This ball is initially uncharged. When it move and touch here, it get negatively charged. Negative charge transfers to the ball. So when the negatively charged ball is existing here, this is positively charged. What will happen? As unlike charges attract, the ball will come towards the X. This is positive, X is positive and this is negative. As the ball is negatively charged, it will attract to the positively charged plate. Then the charge is transferred to the plate X. Then the ball become positive. So when the ball get positive, what will happen next? So the positive ball will attract to the negative plate. So it will move this way. So this process is continue. Y towards Y and towards X. So that's how the shuttling of the ball is occurs. So ball is continually moving between the plates, assuming that the presence of the ball does not affect to the electric field between the plates. That is one assumption. So let's move to the questions. Part A. Explain why the charged ball experiences a horizontal force of constant magnitude. Now, why it is refers to the magnitude, you have to understand the ball experience a force in different directions. From once it is touch Y, it is towards X. Once it is touch X, it's towards Y. So the direction change, but as the charge is same and the electric field strength is same. Why electric field strength is same? As it is an uniform electric field. Why we say uniform? Parallel metal plates which is charged. So let's see. So electric field between x and y is an uniform electric field as E equal V over D. V is constant, D is constant. So field also constant, that is we have learned earlier video that if we draw field lines, then we have to draw it parallel with equispaced. So as F equal EQ, so E constant, if the Q also constant, the force experienced by the charge object also will be constant. That is the final answer, the final argument. Then part B, the ball initially at rest touching plate Y, so we know that, we have read it out. After it leaves the plate Y, the ball accelerates uniformly from plate Y to X. Why it is uniformly accelerate? As the uniform resultant force act. Why uniform resultant force act? As what we have described here. This is a uniform electric field, so E is constant, charge is constant, the force is constant. So it will accelerate with as it experiences a uniform force on it. So the mass is given. We have asked to show the acceleration about 0.2 meters per second square. This also show that question. So here they have asked or request us to show 1 SF. So we have to provide for 2 SF in the final answer. Distance between the plates given, potential difference between plates given, the charge of the ball is given. So we can start working. So as E equal V over D, field strength is potential difference divided by the distance. So potential difference is no problem, it is same unit, we can substitute as it is voltage, but the separation is given in centimeters, so we have to convert centimeters into meters for this E equal V over D equation, because the unit that should come for D is meters. So we have converted by dividing centimeters by 100. So we have the final figure for the electric field strength. So then we can have the relationship of F equal EQ, the resultant force we need. So we have calculated the field strength and we have the charge, but it is given in nanocoulomb. But keep in mind, whether it is nanocoulomb, micro, whatever, for the substitution of F equal EQ, the Q unit should be coulomb. So we have to convert or transfer the value correctly, appropriately to the coulomb. So it has been done here, and the final answer for resultant force or the electrostatic force is 5.79 into 10 to the power minus 4 Newton. So we have the electrostatic force or the resultant force. Then we can use the relationship of F equal ma, resultant force equal mass into acceleration, and resultant force substitute as the electrostatic force, and mass is given. Mass of the ball is 2.7, that also grams. So for this F equal ma equation, m should be kilograms. So we have to divide 2.7 by 1000 and the answer 0.00027, and acceleration can be calculated. So here request 1 SF, we have to provide it to 2 by looking at the third one also. So final answer, acceleration 0.21 meters per second square. Example 3. A teacher is demonstrating the properties of an electron beam using an electron deflection tube. This is the electron deflection tube. So you may familiar or not familiar, don't worry. You can understand what it is. In the tube, now this is the description. In the tube, the path of a beam of electron. In the tube, the path of a beam of electron can be observed on a grid. So here it's not there, but here it is observed. Now electron beam is entering and you can see the deflection. The grid is positioned. Now grid is positioned. This is the squares you can see, that is what you call grid position between the two metal plates. This is a metal plate, this is another metal plate. And there is a potential difference. So if two metal plates fixed parallel with potential difference, we have to understand that is, what is that? Uniform electric field, uniform electric field. So where the electrons are entering, that's the knowledge or the know-how that you should have. Now electron is entering to the uniform electric field. So what is the behavior? So the electron beam undergoes a vertical deflection. Now here it is, if it undeflected, then this must be the path A. So there must be a vertical deflection of 2 centimeters, vertical displacement of 2 centimeters. After traveling a horizontal distance of 8 centimeters. So what is this horizontal distance? This horizontal distance is 8 centimeters and there are 2 centimeters vertical deflection. Calculate the velocity with which the electrons enter. Now we have to find out the entering velocity, how the electron beam enter horizontally. It's enter horizontally. So what we have to find out as the initial horizontal velocity, where in what the electrons enter to the electric field. So another two informations given, so that I have highlighted them in blue. This is one information, this is another information, and now the potential difference between the plates, 1.5 kV, so kilovolt. So when we are using, you have to convert it to volts by multiplying by 1000, and distance between the plates, that the separation of the plates, so that is given in centimeters. So we have to keep in mind, need to convert it to meters by dividing divide by 100. So now to calculate the entering velocity, that is initial horizontal velocity, the electron beams enter. So these are our working steps. First, what we should have an idea F equal EQ and E equal V over D to find the force. So V over D, this information is given, potential difference between plates given, and separation given. So when we have E as the charge also given, we can find the force. So as we have the force, we can find the acceleration along the field lines, not horizontally. The vertical component acceleration we can find. So then, as they have given the vertical displacement and the horizontal distance that it traveled, so we can use the motion equations S equal ut plus half at squared with vertical displacement concerned. If we consider this with vertical displacement, you have to understand that vertically, when initial velocity does not have vertical component, because initially it is entering horizontally. So when we resolve horizontal component into vertically, this becomes 0. So no value for this. So you have to understand that S equal half at squared will be the vertical displacement. Then from that we can find T, and then apply horizontally also the same thing. When we apply horizontally there won't be any acceleration. So this part becomes 0. So then it is horizontal displacement is equal ut. Then we can find out u. Okay, let's work. So first instance, we have to find the force. To find the force, that is EQ, E is V over D. So V value is given, that is 1500 volt, but as given as 1.5 kV. Now we have to convert it to volts by multiplying 1000. So the distance or separation is given in centimeters, we have to substitute in meters and multiply it by the charge. So we get the force as 4.8 10 to the power minus 15 Newton. Then we use that to find the acceleration. So we have calculated the force, and the mass of acceleration is substitute, which is given in the formula sheet, and we can have the acceleration as 5.26 into 10 to the power 15 meters per second square. So we apply, as mentioned earlier, we apply the S equal ut plus half at squared vertically upward. So when we resolve initial horizontal velocity as it enter horizontally, when we resolve 90 degrees to make it horizontal, then u becomes 0. So this component, this part becomes 0. So it becomes S equal half at squared. S, that vertical displacement they have given in the question as 2 centimeters. So here it become 0.02 meters. We have to convert it to meters, and half A we have calculated. So we substitute the values and T squared, and we can find out T. What is this time? The time taken for the electron beam to have 0.02 meter vertical displacement. So the same time, as they are independent, the same time it will take to cross the tube of this length, that is cross this length. When this have a displacement of this much, it has traveled at the same time this much of distance horizontally. So we have to use the same equation horizontally. So then horizontally there won't be any acceleration because the field is perpendicular. So acceleration becomes 0, so this part becomes 0. So then it comes as S equal ut. S is given in the question, and u we have to find out initial horizontal velocity, and t we have obtained there. So the final answer, horizontal initial velocity, will be 2.9 into 10 to the power 7 meters per second. So just we'll have a look and compare the electric field strength and the gravitational field strength. So definition is force per unit charge, electric field strength, force per unit mass on gravitational field strength. But we have familiar from the O-level class. So this also here, the force what we concern is the small positive test charge, and here small test mass. So the relationship is a little bit similar. Here force over charge, here force over mass. So this is electric field strength, this is gravitational field strength. The unit NC minus 1 Newton per Coulomb, Newton per kg. Both are vector quantities, so they have magnitude and direction. Electric field strength, if we look into the electric field strength again, that is force act on unit positive charge placed at whatever the point. So this relationship, we have learned 3 relationships for the electric field strength. So what we have to stress in our minds, when to use the relationship. Now this relationship E equal F over Q can use at any place. E equal V over D can be used only in uniform electric fields. E equal KQ over R squared can be used only in radial fields. So according to the situation, appropriately we have to select the correct relationship and apply. That is very, very vital and very, very important to keep in mind. So let's summarize what we have learned. That is, we use the E equal KQ over R squared equation and learn how we have obtained that for the electric field due to a point charge, and we apply E equal V over D for uniform electric field between the 2 parallel metal plates. And another thing that we have come across is energy transferred in electric field. When a charge is moved in a potential difference, work is done that is equal to gain in kinetic energy as the particle accelerates due to the electrostatic force act on the charged particle. So thank you, and we'll meet again in another video show.